Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started.
Have you ever watched a drone zip through the sky or hover perfectly still, seemingly defying gravity, and just find yourself wondering, how does it do that? Or maybe you've tried flying one yourself, feeling that familiar frustration as the battery drains faster than you expected.
Oh, yeah. Definitely been there.
Well, today we're taking a truly fascinating journey into the unseen forces and clever engineering that make drones fly, specifically focusing on two core pillars: propeller thrust and efficiency.
It's a topic that, from a distance, might appear straightforward, but the underlying principles and practical nuances are incredibly rich.
Right.
Our goal in this deep dive is to unpack the fundamental physics that allow propellers to generate force, then dive into the nitty-gritty of why motors don't convert all their electrical power into useful work,
Yeah, the heat loss problem.
Exactly. And finally, explore the myriad of factors, everything from the subtle curve of a prop blade to the density of the air around it, that dictate how efficiently your drone operates. We want to equip you, our curious listener, with a really solid, actionable understanding, moving beyond just knowing formulas to truly grasping what's going on beneath the surface of every flight.
Exactly. Think of this as your shortcut to being genuinely well-informed. Whether you're building your own drone, you just love dissecting how things work, or maybe you need to understand these mechanisms for your professional life.
Yeah, absolutely.
We've pulled some incredible insights from diverse sources: the fantastic LabRat Scientific and Taito Robotics YouTube channels.
Excellent resources.
Alongside detailed articles like Propeller Dynamics and Drone Efficiency Fundamentals, Propeller Thrust and Efficiency Trivia, and some really practical, real-world drone scenarios.
Good stuff.
So let's get started and discover the secrets behind efficient flight. Okay, let's unpack this. So let's start with the absolute basics. We see propellers spinning, creating that seemingly magical lift. But what exactly is a propeller doing at a fundamental physics level to create that force? What's the core principle at play here?
What's truly fascinating here is that it all boils down to one of the most foundational laws of physics, a concept many of us encountered in school: Newton's third law of motion.
Ah, okay. Action-reaction.
Precisely. The principle, as you might recall, is deceptively simple. For every action, there's an equal and opposite reaction. In the specific context of a propeller, this means it generates thrust by actively pushing a mass of air downwards.
Pushing the air down.
Right. The reaction to this downward force is an equal and opposite upward force, and that is precisely what lifts the drone into the sky.
Makes sense.
Think of it like a swimmer in the water. To move forward, they push water backward. The harder and faster you push that water, the faster you move through it.
Okay, good analogy.
Propellers are doing essentially the same thing, but instead of water, they're pushing soup. That is, air backward, with incredible precision and force to create forward or upward movement.
Pushing soup, I like that.
Our source material from LabRat Scientific takes this concept a step further and explains it perfectly through the lens of momentum.
Momentum, okay. Mass times velocity.
Exactly. At its core, it's simply mass multiplied by velocity. So in SI units, that's kilograms times meters per second. The key to understanding this propeller action is to imagine what engineers call the actuator disc.
Actuator disc. Like an imaginary circle?
Yeah, pretty much. It's a thin imaginary disc that represents the area swept out by the spinning propeller blades as they rotate.
Gotcha.
Think about the air above this imaginary disc. It has essentially zero momentum. It's not really moving in any particular direction relative to the drone.
Right, it's just sitting there.
But as the propeller spins and interacts with that air, it imparts a significant velocity to it. This creates a high-velocity flow with considerable momentum on the bottom side of the propeller.
So it speeds the air up downwards.
Correct. It's this crucial change in momentum from low above the disk to high below it, occurring over a very short period of time as air passes through that thin actuator disk that generates the thrust we're talking about.
Ah, that changes the force.
Exactly. In physics, force is precisely this change in momentum divided by the change in time. You'll often see it written as dp/dt. The units work out beautifully. Kilograms times meters per second for momentum divided by seconds for time gives you newtons.
Newtons, units of force.
Which are the fundamental units of force. This isn't just an abstract formula, it's the tangible physics of flight.
That's a really clear explanation of momentum and how that change is the actual force. But, it's one thing to talk about it in theory, but to actually see it demonstrated, like in that lab rat scientific video, that's where the concept truly clicks for me. How did they manage to show something so fundamental so clearly?
It's a brilliant, simple experiment that really solidifies the concept for anyone. What they did was attach a clever reaction plate ingeniously crafted from corrugated cardboard with cutouts covered by poster board to ensure it was as light as possible directly to the drone's landing gear.
A cardboard plate, okay.
Yeah, super lightweight. Their hypothesis was straightforward. If the downward momentum of the air, which the propeller is actively generating, is somehow transferred back into the drone system by striking this plate, then the net upward force should be significantly reduced or maybe even completely nullified.
So if the air hits the plate, it cancels the lift.
Essentially, yes. And the experiment results were quite dramatic. Despite powering up to its usual liftoff throttle, the drone with the reaction plate attached simply could not lift off the ground. It stayed firmly planted, motor spinning furiously but going nowhere.
Wow, really? It just sat there?
Just sat there. The explanation is a direct, undeniable demonstration of Newton's third law and the momentum exchange we just discussed. The upward thrust generated by the propeller, which is trying to push the drone into the sky, is exactly canceled out by the downward force of the air's momentum transferring back into the reaction plate.
And back into the drone itself.
Exactly. Consequently, back into the drone itself. Essentially, the drone pushes air down, which then hits the plate and pushes back up into the drone's structure. The momentum of that air is transferred, effectively acting as an opposing downward force on the drone. The net force on the drone becomes zero, so it remains motionless.
That's amazing.
It perfectly illustrates this fundamental exchange of momentum in a very practical, undeniable way. It's a real aha moment when you see it.
That truly makes the physics tangible. So, we're effectively talking about the propeller as a highly efficient air-moving device. But this raises an important question. Why do engineers often refer to propellers as rotating wings? It's not just poetic, is it?
No, it's far more than poetic. The terminology is fundamentally accurate and points to a deep understanding of fluid dynamics. The Wright brothers, who famously started as bicycle makers, grasped this concept remarkably early on.
Over 100 years ago.
Right. When they were designing their first powered aircraft, they didn't simply copy the design of boat screws, which were common at the time for propulsion. Instead, they realized that propeller blades are essentially airfoils, or wings, that rotate.
Like a wing spinning around.
Exactly. Just like a fixed wing generates lift by creating a pressure difference, as described by Bernoulli's principle, and by accelerating air, a propeller blade does precisely the same thing, but in a rotational motion. This rotational acceleration of air results in forward or upward thrust.
Okay.
What's truly remarkable is that their hand-carved wooden props achieved about 66% efficiency.
66%. Back then.
Yeah. When you consider the technology available in 1903, that's incredibly close to the efficiency levels of many modern drone propellers.
That's nuts.
It speaks to a profound, intuitive understanding of these principles that was far ahead of its time.
That's a fantastic foundation. So we understand how props physically push air using the principles of momentum and rotating airfoils. But that push, of course, comes from a motor.
Right, the power source.
And if you've ever held a motor that's been running hard, you know it gets hot. That heat is wasted energy. This section, drawing heavily from Taito Robotics, is incredibly illuminating on why motors are inefficient and where that lost energy actually goes.
Indeed. Charles from Taito Robotics began his talk by describing a very real-world problem they faced when developing a small, quiet helicopter for tactical police work. It could only fly for a mere 4 minutes.
4 minutes. That's not long.
Not long at all. This incredibly short flight time highlighted a critical need to understand motor and propeller efficiency deeply, not just by applying existing formulas, but by truly diagnosing the root cause of the energy drain. And what they discovered is that the core problem with motor inefficiency, the primary reason for that heat you feel, comes down to electrical resistance within the motor itself.
Just wire inside.
Essentially, yeah. At its simplest, a motor is essentially a coil of wire wound around a core, and any wire, no matter how good a conductor, has some inherent electrical resistance. To illustrate this, Charles used a very clear analogy. Imagine a stalled motor, that is, a motor that's receiving electrical power but isn't allowed to spin.
Like if the prop gets stuck.
Exactly. In the stalled condition, the motor behaves just like a simple resistor. When current flows through it, it generates heat, much like a wall heater or the heating element in a toaster.
Right.
The source material gives a stark example. With a typical 3S battery, delivering around 11 volts, and a motor resistance of, say, 0.3 ohms, a stalled motor can generate a staggering 417 watts of pure heat.
400 watts. Just heat.
Just heat. This heat is pure energy loss. It's not contributing to mechanical work at all. This phenomenon is known as IRR loss, where the losses are proportional to the square of the current.
I squared R. I remember that from physics.
Yep. This means a critical nugget for you. If you double the current to get more torque or power, you don't just double your heat loss, you actually quadruple it.
Whoa.
This drastically escalates the problem of energy waste and is a primary reason for motor inefficiency.
Whoa, that's a massive nonlinear efficiency hit.
Yeah.
So it's not just that motors get hot when you push them. It's that pushing for more power quadrupled your heat loss for every doubling of current. That's a huge factor for anyone thinking about battery life or motor longevity.
Absolutely critical.
So how does a motor actually generate useful torque then? And what's this back EMF I keep hearing about?
Great question. Let's first talk about how a motor generates torque and then introduce the crucial concept of back electromotive force, or back EMF.
Okay.
When current flows through that coil in a stalled motor, it creates an electromagnet. This electromagnet then interacts with the motor's permanent magnets, producing a force or torque that tries to make the motor spin.
Magnetism making it turn.
Right. This torque is directly proportional to the current flowing through the coil and the number of turns in the coil. This immediately presents a trade-off for motor designers. More turns increase torque, which sounds great for lifting heavier loads.
Or power.
But it also means a longer wire, which in turn means more resistance, leading to increased heat loss. It's a balance.
Ah, okay. Yeah. Trade-offs everywhere.
Always. Now, here's where it gets truly interesting. When the motor is moving and spinning, the magnet moving within the coil generates its own voltage potential.
Like a tiny generator inside.
Exactly like a generator. This is called back electromotive force, or back EMF. Think of a no-load condition. If the motor spins so incredibly fast that the back EMF voltage it generates precisely equals the battery voltage that's supplying it,
if they match,
then effectively no current flows to the motor's internal resistance, and consequently no net torque is generated. This is what happens if you spin a motor with no propeller attached. It draws minimal current, generating minimal torque, even though it's spinning very fast.
Right, because there's no load fighting it.
Precisely. In a real operational scenario, somewhere between the stalled condition and the no-load condition, the battery voltage is effectively split. Part of that voltage is dropped across the motor's internal resistance, generating that inefficient heat we just discussed.
The I squared R losses.
Correct. The other part of the voltage is the back EMF, which represents the useful mechanical power being produced and is converted into the torque that spins the propeller.
So the back EMF is the good part.
That's a good way to think about it, yeah. Our primary goal in efficient drone design is to maximize this mechanical power while simultaneously minimizing the heat generated by the resistive losses.
That makes perfect sense. So we're trying to find that sweet spot between heating up the motor and getting useful work out of it.
Yeah.
How does this interaction between torque and RPM actually look, and how does it relate to the motor's overall efficiency?
This interaction between torque and RPM is best visualized on a torque versus RPM diagram, which Taito Robotics thoroughly explains. Mechanical power, as defined by physics, is simply torque multiplied by RPM.
Torque times speed, okay.
Now, consider the extreme ends of the spectrum again. At stall, you have maximum torque, but 0 RPM, so no mechanical power is actually produced. No useful work is done.
Lots of force, no movement.
Right. Conversely, at no load, you have maximum RPM, but 0 torque. So again, no mechanical power. Mechanical power is actually maximized somewhere in the middle of that torque RPM curve, where both torque and RPM are significant.
Okay, makes sense. Somewhere in between.
Crucially, remember that heat losses are primarily proportional to torque, not RPM. The higher the torque you demand, the higher those IR losses will be.
More torque, more heat.
Exactly. This leads to a distinct efficiency curve. A motor's maximum efficiency occurs along a specific line on the torque RPM graph, and this line is always lower than the line of maximum mechanical power.
Oh, interesting. So peak efficiency isn't peak power.
Correct. This is a critical insight for drone designers and operators. You often have to make a choice between maximizing raw power for speed or heavy lift, and maximizing efficiency for longer endurance or flight time. It's a constant balancing act in design and operation.
So it's a constant balancing act, not just for the engineers designing the motors, but for us, the users, and how we operate them. It sounds like there's a lot going on inside that motor bill. What are the actual physical components that contribute to this dynamic between power and efficiency?
Yeah, if we connect this to the bigger picture, a real motor has several key parts that are all working together in this dance between power and efficiency. You have the rotor, which is the spinning part.
The bell you mentioned.
Often called the bell on the popular outrunner motors that drones use because it literally looks like a bell spinning around the core. Then there's the stator, which is the stationary part, and it's where the coils of wire are wound.
Okay, rotor spins, stator stays put.
Right, and these coils aren't just bare copper, they're made of insulated wires. Without that thin enamel insulation separating each turn, it would simply be a solid copper block, and no electromagnetic field could be generated as intended.
The insulation is key.
Absolutely vital. There's also some important terminology to understand when you look at motor specifications. Most hobby motors, for example, are three-phase motors. You can typically count 3 wires leading into them from the electronic speed controller, or ESC.
3 wires, 3 phases.
Generally, yeah. Poles refer to the number of magnets in the motor, sometimes defined as the number of magnets divided by 2. The coils are, as you might guess, a multiple of the number of phases, so typically a multiple of 3.
Poles and coils. Yeah.
However, the number of poles can be and often is different from the number of coils, and these configurations have subtle but important effects on motor performance characteristics like torque and RPM.
More complexity.
Always more. The electronic speed controllers, or ESCs, are also a critical component in the system. ESCs are what regulate the power going to the motor, acting like a tiny, incredibly fast computer that switches power on and off to the coil.
Motor's brain, sort of.
Kind of, yeah. They do this by using very fast-switching transistors. 2 key settings on ESCs are particularly relevant to efficiency. One is timing. This refers to how early or late the electrical pulse is sent to attract the magnet.
Timing, like engine timing.
Similar concept. If you fire the pulse earlier, it tends to increase the motor's kV, which is its RPM per volt, a measure of how fast it spins for a given voltage, but can reduce the maximum torque it produces.
Faster spin, less grunt.
Right. Conversely, if you fire late, it can increase torque but reduce the kV. For example, drone racers might use dynamic timing to always achieve maximum power for blistering speed.
Max power.
Whereas endurance flyers might use a different timing setting to keep the motor operating in its most efficient region for longer flight times.
Optimized for the mission.
Exactly. Another factor is the switching frequency, how often those transistors in the ESC switch. More frequent switching, while sometimes providing smoother motor operation, can lead to more resistive losses within the transistors themselves, subtly reducing overall system efficiency.
Even the ESC isn't perfectly efficient.
Nothing is, unfortunately. Finally, we must consider thermal limitations. Real-world motors cannot sustain maximum current indefinitely, especially when stalled.
Like we talked about with the heat?
Precisely. If you were to send maximum current to a stalled motor, it would quickly overheat and burn out, as Taito Robotics demonstrated in their research. There's a practical physical limit to how much torque you can generate and for how long before the motor's thermal capacity is exceeded.
Don't cook your motors.
Pretty much. So while the theoretical performance curves might show higher power, the real motor has a physical ceiling dictated by its ability to dissipate heat. This is why managing current draw is so vital for both efficiency and the lifespan of your components.
So it's clear. Motor efficiency is a critical piece of the puzzle, a constant battle against heat and electrical resistance. But once the motor is doing its job, that power is transferred to the propeller.
Right, to the air mover.
It's the part that actually touches the air, after all. And I've seen so many different types. How does the propeller itself factor in? What do all those design choices actually do?
Precisely. Now that we understand the intricate workings of the motor, let's turn our attention to the propeller, the actual component that interacts directly with the air to generate thrust. Its design, right down to the subtle curve of its blades and the environment it operates in, have a monumental impact on overall flight efficiency.
Okay.
This raises an important question. What propeller characteristics directly impact thrust and efficiency? Let's break down the key design elements that make a difference.
Let's do it. Pitch first.
Good place to start, pitch. This is often defined as the distance a prop would theoretically move forward in one revolution if it were cutting through a solid medium, like a screw thread moving through wood or the sky.
Like a screw in the air.
Yeah, basically. So a 6-inch pitch prop would theoretically move 6 inches forward for every single turn. The pitch choice has profound implications. Low pitch props are generally ideal for slow flight, stable hovering, and maximizing endurance.
Good for cameras.
Exactly. They're excellent for photography drones where smooth, long flights are paramount. High-pitch props, on the other hand, are designed for speed, much like a propeller on a high-performance aircraft.
Racers.
Right. But, and this is a key takeaway, they demand significantly more current from the motor and inherently sacrifice efficiency in the process. This is why you see them on FPV racing drones, where raw speed and agility are paramount, and short flight times are an accepted trade-off.
Speed costs battery.
Always. Looking to the future, variable pitch props, which are already being tested on larger, more advanced drones, will likely become more common. These clever designs automatically change their pitch for maximum efficiency across different flight regimes.
Like on a big airplane.
Much like the sophisticated multi-position propellers on manned aircraft. Imagine a drone that can be super efficient for hover and then instantly optimize for forward speed without needing a prop swap.
That would be cool. Okay, what about diameter? Bigger is better?
Well, generally, yes, diameter is another crucial factor. As a general rule, larger diameter props tend to be more efficient. They can move a greater volume of air at lower RPMs, which means less energy is lost to turbulence and frictional drag.
Move more air slowly.
Right. However, there's a significant trade-off. Larger props require substantially more torque from the motor to spin them. If not matched correctly, they can easily overload motors, leading to inefficiency and potential damage.
Got to match the motor and prop.
Absolutely crucial. A fascinating real-world example of this principle is human-powered quadcopters.
Human-powered, really?
Which use enormous slow-spinning propellers to achieve the maximum possible kilograms of thrust per watt. They're optimizing for the extremely limited power output of a human, so maximizing efficiency through large, slow props is absolutely critical.
Wow. Okay, so pitch and diameter. What about the number of blades? 2, 3, 4.
Good question. Blade count. This is another area of trade-offs. Generally, more blades mean more thrust, as there's more surface area interacting with the air.
More bite.
But it typically comes at the cost of efficiency. The reason? Increased drag and the generation of more helical vortices, which are essentially spirals of turbulent air shed from each blade tip that interfere with each other, creating wasted energy.
More blades, more turbulence, less efficient.
Often, yes. This wasn't always the primary concern in aerospace, though. Historically, during WWII, fighter planes like Spitfires and Mustangs evolved from 2-blade to 3, 4, and even 5-blade props.
Yeah, I've seen pictures.
Not primarily for efficiency gains, but because they needed to absorb more engine power within a limited propeller diameter. They needed to put more horsepower to the air, and adding more blades was the way to do it, even if individual blade efficiency suffered slightly.
Needed the thrust.
Exactly, needed the power transfer. Finally, tip speed and the Mach limit are critical, especially for high-performance drones.
Going supersonic.
Almost. As the tips of a propeller blade approach the speed of sound specifically, around Mach 0.85 to 0.9 drag skyrockets, efficiency crashes dramatically and noise explodes due to what are called compressibility effects in the air.
The air can't get out of the way fast enough.
Basically, yeah. The air molecule's literally struggling to get out of the way. While most common drones don't reach this, some racing drones do fleet with this limit, purely for the thrill of raw speed and aggressive maneuvers, not for efficiency.
Noise and wasted energy.
A lot of it. You can even find historical anecdotes of WWII bombers with huge props that sometimes created visible vapor cones at their tips due to these high speeds, a clear visual indicator of energy being lost to supersonic effects.
Incredible. That's amazing how much thought goes into just the prop's physical design. But you also mentioned the environment it flies in. How much does something like the weather or even being close to the ground affect a drone's efficiency?
Oh, it affects it profoundly. Beyond the propeller's physical design, the environmental impacts are profoundly important because air is the medium the prop is working against.
Right, the soup.
Exactly. Air density, for instance, is a huge factor in how much bite a prop gets. At higher altitude, the air is thinner, meaning props have less air to bite into, producing less thrust. Less air to push against.
Right. This forces your motors to work harder, drawing more current and draining your battery faster, and you'll notice you need significantly higher RPMs just to hold a stable hover.
Need to spin faster.
Similarly, temperature plays a crucial role. Cold, dense air provides more thrust, which is why manned aircraft often climb better in winter. Conversely, hot, thin air reduces thrust, making flight more challenging and less efficient.
Hot days are harder.
Yep. And here's a counterintuitive but important point about air density. Humidity. Humid air is actually less dense than dry air.
Wait, less dense. How?
Because water molecules, H2O, are lighter than the nitrogen and oxygen molecules, N2O2, they displace in the atmosphere.
Ah, okay, lighter molecules push out heavier ones.
Precisely. So on a hot, humid day, your props will perform worse than on a cold, dry day, even at the same altitude. When you combine high elevation with hot weather, you get density altitude, which describes a much thinner air environment, leading to significantly less available thrust overall.
Density altitude. Gotta watch out for that. Absolutely. This is a critical factor for serious mission planning. Then there's ground effect. Just like helicopters, drones experience a temporary boost in thrust when operating near a surface.
Flying low.
Yeah, typically within 0.5 to 1 propeller diameter above the ground. While it temporarily boosts thrust, it also makes the airflow turbulent and can destabilize hover control.
So it helps, but makes things shaky.
Kind of. The efficiency in this zone is weirdly distorted, making precise control more challenging for autonomous systems or even a human pilot trying to maintain a steady hover.
Okay. What about prop wash?
Right, propeller wash, or the slipstream effect. This also comes into play. The column of high-velocity airflow, the slipstream, generated by spinning props can interfere with onboard sensors, payloads, or even other propellers on the same drone.
The air blowing down hits things.
Exactly. This is particularly relevant for coaxial drone designs, which feature stacked props, one directly above the other on the same motor axis. The lower prop in such a setup operates directly in the disturbed, turbulent slipstream of the upper prop.
It's flying in dirty air.
Precisely. Leading to inherent efficiency losses because it's not working with clean, undisturbed air.
So it's not just the prop itself, but the air it's moving through, and even how close it is to the ground. That's a lot to consider. What other critical, perhaps less obvious factors are impacting efficiency that we should know about?
There are indeed several other critical factors, some of which are often overlooked but have a huge impact. First, propeller balancing is far more important than just reducing vibration.
Jello in the video, yeah.
Well, beyond that, an unbalanced prop doesn't just shake. It actively reduces thrust efficiency because the motor is constantly fighting that imbalance, creating wobbles that waste energy.
Wasting power, just shaking.
Exactly. This stress also significantly lowers the lifespan of motor bearings and, crucially, can corrupt sensor data from the IMU, that's your inertial measurement unit, which measures orientation and acceleration, or GPS, leading to unwanted drone drift or unstable flight.
Messes with the drone's brain.
As the saying goes in the drone world, a wobbly prop is a lying sensor. You can't trust your drone's brain if its props are shaking it up.
That's a good one. Okay, balancing is key. What else?
We also have to understand induced versus profile drag. Induced drag is the drag that specifically comes from creating lift or thrust.
The cost of lift.
Right. And it's dominant at low speeds, such as during hover or takeoff. Think of it as the energy cost of moving air downwards to stay up. Profile drag, on the other hand, is the skin friction and form drag on the propeller blades themselves, and it becomes dominant at high forward speeds as the prop slices through the air.
Drag from the blade shape and surface.
Correct. Every propeller has an RPM or airspeed range where it's most efficient, a sweet spot where the combined effects of these two types of drag are minimized.
The efficiency sweet spot.
Yeah. Below this range, induced drag dominates. Above it, profile drag takes over. This means that propeller efficiency is actually lowest at hover, where the drone isn't moving forward, meaning the useful thrust horsepower, or THP, is technically 0, and also at very high forward speeds.
Lowest at hover. That's surprising.
Well, you're generating thrust just to stay still, no useful work in terms of movement. Makes sense thermodynamically.
Okay, I see. What's this figure of merit thing?
Figure of merit, FOM, is a specific dimensionless measure of hover efficiency for rotorcraft, essentially telling you how well a propeller converts power into useful thrust in a hover.
A score for hover efficiency.
Basically, high-quality, well-designed propellers might achieve an FOM of around 0.7, while cheaper plastic props will have a significantly lower FOM, indicating less efficient hovering.
So 0.7 is pretty good.
Relatively, yes.
Okay.
The precise engineering of a propeller also includes blade twist. Real propeller blades are not flat, they are twisted from root to tip.
Yeah, you can see that curve.
This twisting is essential to equalize lift along the entire length of the blade and boost efficiency. The inner section of the blade moves slower and therefore needs a higher angle of attack, AOA, to generate sufficient lift.
Needs more bite closer in.
While the outer section moves much faster and requires a lower AOA to prevent excessive drag and maintain efficiency. It's a subtle but critical detail for aerodynamic performance.
Clever design. Does the material matter? Plastic versus carbon fiber.
Oh, hugely. The material a propeller is made from, such as carbon fiber, also makes a big difference. Stiffer blades, like those made from carbon fiber, flex significantly less under aerodynamic load.
They hold their shape better.
Exactly. This leads to more consistent thrust and efficiency and also reduces vibration, which is beneficial for sensitive sensors and camera gimbals. Flexible plastic props, however, can twist and deform under load, which reduces their intended aerodynamic shape and consequently their efficiency.
Like a floppy oar.
Good analogy. Think of trying to paddle a boat with a rubber oar versus a stiff wooden one. Finally, propeller noise is not just an auditory annoyance, it's a direct indicator of wasted energy.
The buzzing sounds.
Yep. The classic buzz or whine of a prop is turbulence shedding off the blade tips. Quieter props are generally more efficient because less energy is being dissipated as sound and turbulence, and more is being converted into useful thrust.
Quiet equals efficient.
Generally speaking. It's an interesting tidbit that Hollywood sometimes fakes drone sounds in films because real, efficient drone props can be surprisingly quiet, which often doesn't make for dramatic cinema.
Huh. Too quiet for the movies. That's an amazing level of detail, from the molecular level of air density to the specific material of the prop itself. This is where the rubber meets the sky, so to speak.
Good phrase for it.
Understanding these factors isn't just academic. It's about making smart decisions in the field that directly impact how long your drone flies or how well it performs its mission. So what are some practical implications for us as operators or enthusiasts? What are the key takeaways we can apply to real-world drone operations?
This is precisely where knowledge is truly valuable when understood and applied. Many real-world drone scenarios highlight the critical trade-offs that operators constantly face between achieving their mission goals and maintaining efficiency.
The balancing act again.
Always.
Yeah.
One fundamental concept that ties into all these decisions is the thrust-to-weight ratio. This is a golden number for multi-rotors. A safe ratio is generally considered to be at least 2.1.
Twice the thrust as weight.
Right, meaning the maximum thrust your drone can generate should be at least twice the aircraft's total weight. Anything lower leads to sluggish climb performance, poor resistance against wind, and can quickly become unsafe, leaving you with little margin for error or emergency maneuvers.
Need that extra power margin.
Definitely. Another crucial principle and a definite nugget to remember is what's often called the power cubed rule. The math behind this states that propeller power draw increases with the cube of the RPM.
Power equals RPM cubed. Wow.
The implication is profound. If you double your propeller's RPM, you actually need 8 times the power to do so.
8 times.
Yeah. This is why endurance-focused drones are designed to spin large-diameter props relatively slowly, rather than using smaller props that spin very fast. It's an easy concept to remember and a critical piece of insight. RPM cubed equals battery subdued.
RPM cubed equals batteries subdued. I'll remember that one.
Understanding this helps you appreciate why even small increases in speed or hover demand can dramatically impact your flight time. For advanced operators, efficiency measurement in the field is a practical, real-time takeaway.
Watching the numbers.
Yeah. By watching the current draw per percentage of throttle on your flight telemetry, you can gain immediate insight into how efficiently your drone is operating. If the current draw climbs sharply for only a small increase in throttle percentage, it's a strong indication that the drone is operating outside its prop efficiency band.
So you can see when it's struggling.
Exactly. This kind of telemetry monitoring is how experienced pilots can spot efficiency losses mid-flight and make informed adjustments, sometimes even saving a mission or preventing a critical battery drain.
Very useful. Okay, let's get into those scenarios. High altitude first.
Sounds good. Consider high-altitude operations, for example, if you're mapping a forest canopy in Banff at 7,000 feet above sea level, or surveying a mountain ridge from 5,500 feet up to 7,800 feet.
Mountain flying.
The immediate problem here is that thin air significantly reduces thrust because the props have less air to bite into. This means your motors have to work harder, drawing more current and draining your battery faster.
Harder work, less air.
Right. You'll also notice a significant rise in the RPM needed just to hold a stable hover, and the drone might feel mushy or less responsive on the controls. The critical decision point is to plan for the highest altitude your mission will reach.
Plan ahead.
Definitely. Before flight, you should consider switching to larger diameter, lower pitch props, which are more efficient in thinner air. And always ensure you maintain at least that 2.1 thrust to weight margin, or even higher, for safety at altitude.
Bigger props, lower pitch for altitude.
Generally, yes. The clear lesson here: altitude equals thin air, which requires higher RPM and significantly reduces efficiency. Ignoring this is a recipe for a short flight or even a crash.
Good advice. What about the opposite? Super cold weather.
Right. Let's look at cold weather inspections, such as inspecting oil pipelines in northern Alberta at -20°C, or conducting a night inspection at -15°C.
-20 per.
Yeah, seriously cold. In this case, the cold, dense air actually increases thrust, which at first glance sounds like a bonus.
Some more thrust. Good.
Well, hold on. This denser air also means motors draw more current to move it, increasing the load. Additionally, batteries suffer in cold temperatures, meaning they deliver a lower effective voltage and capacity.
The battery problem in the cold.
Exactly. This combination can lead to significant motor and ESC stress, or even overheating, despite producing more thrust. Your decision points involve pre-warming your batteries to their optimal operating temperature.
Keep them warm.
And avoiding aggressive throttle inputs, especially in the initial minutes of flight. Crucially, monitor your telemetry closely for current draw and motor temperatures. The lesson: cold weather offers more thrust, but significantly stresses the entire power system, potentially leading to component damage if not managed carefully.
So more thrust, but more stress.
Yep.
Got it. Heavy payloads. That seems straightforward, just needs more power, right?
Not quite so simple. Let's talk heavy payload, like attaching a new LiDAR sensor for vegetation mapping, or during a drone transport trial, or even just carrying an overloaded battery pack.
Okay.
The problem is that this increased weight means a higher hover RPM, which pushes the props outside their most efficient operating sweet spot, increases induced drag, and drastically reduces overall efficiency.
Pushing the props too hard again.
Right. It's counterintuitive, but sometimes adding a larger, heavier battery can actually reduce your net flight time if the added weight pushes your props into an inefficient operating zone where the power cubed rule really kicks in.
Bigger battery, shorter flight.
Yeah. Because the efficiency drops off so much due to the extra weight forcing higher RPMs, the decision point here is to always calculate your thrust-to-weight ratio, ensuring it's at least 2.1 for a safe margin.
Check the math.
Always. If it's marginal, you'll need to swap to higher thrust props or, if possible, reduce the payload. It's also wise to add payload gradually during test flights rather than all at once to observe its impact. The lesson: payload changes demand new efficiency math. A bigger battery does not always mean longer endurance if it overloads the propulsion system.
Fascinating. Okay, wind. Flying on a windy day.
Yes, windy coastal survey, maybe on the BC coast with steady 20-kilometer-head headwinds, or surveying a prairie field with a strong crosswind.
Fighting the wind.
The problem is that low-pitch props, which are designed for endurance and gentle flight, will struggle to maintain ground speed against the wind. The drone will have to fight the wind constantly, demanding much higher RPMs, which drains the battery much faster than anticipated.
Endurance props aren't good in wind.
Generally not for holding position or making headway, no. Crosswinds add another layer of complexity, as side props have to work harder than others to maintain position, leading to uneven efficiency across the motors and increased energy consumption.
Uneven load.
Right. Your decision point would be to change to steeper pitch props for better upwind performance, or alternatively, shorten your mission legs, especially those perpendicular to the wind direction. The clear lesson is to match your propeller pitch to the mission environment. Those endurance props will simply fail to provide adequate performance in strong winds, turning a smooth flight into a frantic battle.
Match the prop to the conditions. Makes sense. What about the speed demons, FPV and racing?
Right, cinematic FPV shoot or drone racing. The mission goals are entirely different here. These require small, high-pitch props to generate huge thrust at very high RPMs, prioritizing raw speed and agility above all else.
All about speed.
Exactly. The consequence, as you might guess from the power cubed rule, is tanked efficiency and very short flight times, often less than 5 minutes.
5 minutes?
Yeah, sometimes less. Extreme pitch props are also more prone to stall moments if you make sudden throttle cuts, for example, during a steep dive where the prop loses its aerodynamic bite.
Prop stall.
It's tricky.
Can be. The decision points here are to accept the low endurance as a given, carry plenty of extra batteries, and prioritize speed and agility over flight time. It's also vital to monitor your battery's C rating, its discharge capability, to ensure it can deliver the sudden, high current demands.
Need good batteries.
Absolutely.
Thoroughly.
The lesson. Efficiency is a trade-off. Sometimes mission goals like speed and agility definitively outweigh endurance, and you just have to embrace the short flight times. As the trivia notes, racers burn rubber, pilots burn props.
Love it. Okay, what if you damage a prop mid-flight? Clip a twig or something.
Propeller damage mid-mission. Say one prop clips a twig but doesn't snap, or if you replace just one prop from a set. This might seem minor, but an unbalanced prop, even slightly damaged, creates vibration.
The wobbles again. Right. This not only dramatically lowers efficiency by wasting energy and shaking the drone, but it also destabilizes your IMU, your inertial measurement unit, and gyroscope readings, leading to drone drift, unstable flight, and potentially incorrect sensor data.
Lying sensors.
Exactly. Using mismatched props from different manufacturers can also lead to uneven thrust profiles and reduced efficiency across the motors.
Yeah.
In the worst case, catastrophic failure with parts of the prop acting as shrapnel, especially carbon fiber props, is a real possibility.
Yikes.
The decision point is immediate. Land the drone and swap all damaged props. You should always replace pops in matched sets, not singles, to ensure consistent performance and balance.
Replace the whole set.
Always. The lesson. Prop balance equals flight stability, which equals efficiency and safety. It's non-negotiable.
Got it. Last few scenarios. Urban environments, dust, marine air.
Yeah, drones face various urban and environmental challenges that subtly but significantly impact efficiency. For instance, a downtown survey with turbulence around tall buildings means props cycle between unloaded in updrafts and overloaded in downdrafts and vortices,
Choppy air.
leading to big, unpredictable efficiency swings as the motors constantly adjust. A construction site dust environment means dust can coat the leading edges of your props, subtly roughening the surface and dropping efficiency over time.
Like dirt on a wing.
Exactly. For marine operations, salt air corrodes props and motors, and humidity subtly affects aerodynamics, slowly eroding efficiency over time. And in a hot desert flight scenario, the hot, thin air results in low thrust, requiring higher RPMs, which can significantly increase ESC and motor temperatures, stressing the system.
Heat and thin air again.
Right. The overarching lesson from these varied scenarios, the operating environment significantly impacts efficiency and system stress in ways you might not immediately consider.
So many factors. And finally, changing props mid-project.
This just reinforces the point about matching props to the mission. Propeller changeout mid-project illustrates the need for flexibility and forethought. If you're on a multi-day project where day 1 is endurance mapping and day 2 is fast chase filming.
Different needs.
Exactly. Using endurance, low-pitch props for speed filming will result in the drone struggling and performing poorly, draining the battery rapidly. Conversely, using speed, high-pitch props for mapping, will dramatically reduce your endurance and require far more battery swaps than necessary.
Wrong tool for the job.
Precisely. The decision point is to carry different prop sets for different mission profiles and be prepared to swap them out. The clear lesson: one-size-fits-all props don't exist. Efficiency is always mission-specific. Knowing this saves time, money, and frustration.
Wow. This has been an incredibly detailed look at the mechanics and practicalities of propeller efficiency. It truly feels like every decision, from the manufacturing floor to mission planning, affects performance.
It really does. It's all interconnected.
But beyond the hardware and the immediate flight operations, how is our understanding of these things changing, especially with new regulations coming into play? It feels like the goalposts are always moving.
You're absolutely right. The regulatory framework and the training expectations for drone operators are evolving rapidly, hand in hand with the drone technology itself. We've moved significantly from the early days of remotely piloted aircraft system, or RPAS, training.
Yeah, how so?
Let's trace this evolution of RPAS training as described by Transport Canada. In the early days, pre-2019, training materials like TP15263 focused on fundamental aerodynamics. This included basic concepts like how propeller pitch affects performance and the general generation of thrust.
Just the basics.
Right. However, it didn't really deep dive into advanced metrics such as shaft horsepower, SHP, which is the power delivered to the propeller, or thrust horsepower, THP, which is the power actually converted into thrust, nor did it cover more nuanced concepts like advance ratio or figure of merit. It was about getting the basics right, but not necessarily the deeply analytical. Fast forward to today, and especially looking at 2025, drones are increasingly deployed in high-stakes, complex operations. Think beyond visual line of sight, BVLOS flights, operations in challenging environments, and the use of heavier, more sophisticated drones.
More complex flying.
Exactly. This shift has necessitated a much more detailed, competency-based training model. The new TP15530 guide, specifically for Level 1 complex operations, now emphasizes a much deeper grasp of aerodynamic theory. This includes understanding prop characteristics under varied environmental and performance scenarios, not just in a theoretical vacuum.
Need to know the why now.
Pretty much. This isn't just an academic exercise. It's about practical readiness and making informed decisions in critical situations. These changes are further underscored by recent regulatory enhancements.
I think new rules.
Yeah. Notable CARs, Canadian aviation regulations amendments, like the SOR 2025-70 regulation, have expanded the scope of allowable operations. This now includes BVLOS, extended visual line of sight, EVLS, and operations with medium drones under VLOS.
Opening things up.
Right. This expansion directly increases the importance of truly understanding propeller efficiency, the subtle yet profound effects of density altitude, and the critical performance trade-offs we've been discussing. The message is clear. As of 2025, Transport Canada expects you to engineer your flights, not just fly them.
Engineer your flights. That's a higher bar.
It is. It's a call for a more analytical, informed approach to every mission, requiring pilots to truly understand the physics they are commanding. Looking ahead to what the future holds, we can anticipate several trends.
Okay, what's next?
There will be an increased emphasis on efficiency and analytics. Future assessments for drone pilots will likely test their understanding of nuanced performance factors, such as making precise density-altitude adjustments, calculating power-to-thrust efficiency ratios, and engaging in sophisticated predictive flight planning using real-time data.
More data, more analysis.
Definitely. It moves beyond theoretical recall to applied analytical skills. The broader adoption of competency-based training, CBT models, means that future exams will prioritize decision-making under realistic, often dynamic conditions.
Accepting real decisions.
Right. Understanding efficiency will no longer be just academic knowledge. Pilots will be expected to actively use it. This means being able to adjust prop selection on the fly for a given mission, effectively manage thermal loads on motors and ESCs based on telemetry, or accurately estimate endurance based on changing environmental factors.
Using the knowledge in the field.
Furthermore, evolving technology will naturally lead to evolving requirements. As new technologies emerge, like quieter, more efficient propellers, or sophisticated variable pitch prop systems, or even integrated diagnostics that provide real-time efficiency data directly to the pilot.
Smarter drones.
Operators will need to grasp both the baseline physics and how these new technologies integrate into system-level performance. This constant innovation means a constant learning curve for anyone serious about drone operations.
Gotta keep learning.
Always. Ultimately, regulations will continue to follow capability. As propeller technology advances and drone operational capabilities expand into new spaces, whether it's operating routinely in the upper atmosphere or even potentially in entirely new mediums like underwater.
Underwater drones.
Potentially. The Canadian aviation regulations, CRRs, will undoubtedly continue to evolve. This might include adding concepts like adaptive pitch control or specific efficiency certifications to the RPAS regulatory framework, ensuring that pilots are equipped with the knowledge to safely and effectively operate these increasingly complex machines.
So what does this all mean for us as operators and enthusiasts? It sounds like the deep dive into these concepts, from fundamental physics to practical application and future regulations, is only going to become more critical and, frankly, more rewarding.
Absolutely. What's truly fascinating here is that understanding propeller thrust and efficiency isn't just about memorizing formulas or technical specifications. It's a holistic blend of fundamental physics, meticulous engineering design, and an acute awareness of the dynamic environment your drone operates in.
Physics, engineering, environment, all tied together.
It's truly a blend of science and art that comes to life every time a drone takes flight. This comprehensive understanding informs every single decision, from choosing the right propeller for a very specific mission profile to ensuring the long-term safety and longevity of your drone's components. It empowers you to be a more effective, safer, and ultimately more successful pilot.
It's truly empowering to understand the why behind the what, isn't it? From those tiny coils in the motor battling resistance to the intricate dance of air around a spinning blade, every detail affects how our drones perform and how long they stay in the sky.
Yeah, it really changes how you look at them.
This deep dive should give you a whole new appreciation for the engineering marvels that are propellers and motors, and how critically they impact every single drone flight.
This raises an important question for you, the listener. Given the rapid evolution of drone technology and regulations, how might our understanding of these fundamental principles need to adapt as variable pitch props become standard?
Good question.
Or as drones operate routinely in entirely new environments, like the upper atmosphere where the air is incredibly thin, or even underwater, where the very soup they push changes entirely. What new efficiencies or challenges will that bring to the fore?
A great thought to mull over. We hope this deep dive has given you some incredible nuggets of knowledge and perhaps even inspired you to look at the drones around you with fresh, informed eyes.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.